So today we're going to do partial derivatives and tangent planes. Alright, now let me so again we have a function in 3D. What I've attempted to do here is this is sort of an umbrella, okay, but not entirely round. It's curvy from both sides. This is point x naught and point y naught. All right. So we have these two lines. Let me call this one L X and this one L Y. Okay, now draw on this plane such that on this line value of y is constant at y naught, and on this one value of x is constant at x naught. This black one is tangent to this plane, okay, in 2D should help x and z and y and z. Okay, so we have this in 2D, and all along this value of y is constant. This is this one. Okay, so this plane, and we have a point x naught, and all along this y naught is constant. So although we don't have y on this plane, but you can still do that. Doesn't make difference. And I should do this by black. Let's call this k of y. Along this curve value of y is constant, along this curve value of x is constant. Let's call this k sub x, and similarly along this line value of y is constant, along this one value of x is constant. Okay, this is the deal. Is the message clear? All right. Now, what's the slope of this tangent line? And it's a straight line, it's constant. The slope of this tangent line is, okay, this is partial derivative of the function with respect to y. We're holding k constant. K is constant along this. So this is f prime of y with respect to xy but x is held constant. Okay, now because the slope is constant and it's numerically this point, we can put a subset of y as well. Okay, similarly, the slope of black line is f prime of x, and because it's evaluated, okay, and straight line is across. Along this curve, what we're going to have is, if we take here, okay, then this would be f prime of x, y naught is held constant along this, x would have a different value. Okay, so x would have different value all across, y would have different value all across. These are partial derivatives. Okay, now these are two lines, it's like straight, and they are crossing this. It's like this. Okay, so what I can do is I can put a plane on top of this. So whenever two lines cross like this, in whichever direction, I can put a plane on this. That would be the tangent plane to this function, which is slightly curvy at point x naught y naught. Okay, and although again this is not exactly, but it's something like this, curvy. So what I can have is, I can have a point where it's one direction is going like this, in another it's going like this. On top of this, I can plane which touches at that one point to the curvature. That's the tangent plane. What we'll attempt to do in this session is we'll attempt to get equation of that tangent plane. Okay, now my drawing skills have allowed me to do this relatively reasonably, but beyond this, the next one is difficult. The diagram of the tangent plane. Okay, this is not something which is really giving out the view in 3D, but again, this is how it is. Z, Y, and X. We're going to attempt to find a equation of this tangent plane. At point, let's call this point the same, these are essentially the same diagrams that I've drawn. This one P with coordinates x naught, y naught, and f of x naught, y naught on the z-axis. Alright, now let's proceed. This is a diagram from Sitter. I have reproduced it exactly as it is in the text. Okay, now this is our simple function, one variable. How do we get the line equation for this line, which is a tangent to our function at point x naught, and this one would be f of x naught. Okay, should have done this. For this is, if I may use this, y minus y naught, or you can alternately do it, f of x minus f of x naught is equal to m of x minus x naught. Okay, in this form. Now m here is the slope, so I can replace that with f prime of x naught. Okay, now we're going to use this equation, and then we'll try to get equation of the tangent plane. Okay. The equation of the tangent plane is given by this expression, y minus y naught plus c z minus z naught equal to 0. Okay, in terms of our earlier diagrams, okay, these are also planes, but I have, okay, no, this is not the right x is to double up. This is in front of us. Okay, this one is parallel to the xy plane, this one is parallel to the xz plane, and this one is parallel to the yz plane. Okay, they're also planes. Our tangent plane would again be a plane. The difference is, if I may compare it 2D, we have x, fx, we have a curve, and then we have a line which is tangent to the function at one point, and this f nothing and this. Okay, so these planes are the counterparts of these diagrams in 3D. The tangent plane is a counterpart of that one. Okay, so till here there's nothing which is touching here. Now this one is parallel to two axes. It's parallel to the z-axis and it's parallel to the x-axis. The plane, wherever it's parallel, the coefficient of that one would be 0. Okay, so this should be with a is equal to 0, a is equal to 0, and c is equal to 0. This is parallel with the x-axis and z-axis, so this should be b into y minus y naught equal to 0. B goes to the other side, becomes 0, y is equal to y naught. So this is y is equal to y naught. Similarly, we would have this plane, the equation of this plane would be x is equal to x naught and z is equal to z naught. Okay, so we're just proceeding from these diagrams. Now we have a general equation. This equation can describe any plane in any direction. So if we have, if I may use okay, this one is like this one, that one is like this standing. So we can have the equation of any plane in any direction. Okay, but again it's a plane, it's well, okay. For c not equal to 0, we can write this equation as let me write it here, z minus z naught is equal to minus of a by c into x minus x naught minus of b by c into y minus y naught. Okay, and let's simplify it by saying where a is equal to minus a by c and b is equal to minus b by c. Okay, so this is what we're going to look at from here. Let me write this one on the top, z minus z naught equal to a x minus x naught plus b y minus y naught. Okay, now let me use black. Let's first work towards determination of a. First try to determine a. Okay, consider line L of y. Okay, what's the slope of L of y? And it's a straight line. Slope is constant. Okay, this is f prime of x at x naught y naught. Okay, this is L of y is constant and y naught, and we're differentiating, partially differentiating this with respect to x, and we're putting that value. Okay, now there are two features about this line. This one. First, that the value of y is constant at y is equal to y naught, and second one, let's look at it in 2D. So we have x and z, and we have this what we call k of y, and we have this line L of y. this is y. Okay, this is k of x and this is k of y. I'm just drawing this curve and this line here. The plans are x naught, and since everywhere on these line y is constant and y naught, we can just put y naught, and we have f of x naught y naught here. So what's the line of this equation of this line? The equation of this line would be whatever is on the variable on the vertical axis minus the value of that variable, z minus, and we can just call it z naught. Z minus z naught equal to the slope of this function, which is f prime x naught y naught, multiplied by x minus the value that x takes. Okay, I started with this. So we've just replaced y, which was earlier on the vertical axis, with z, which is now on the vertical axis. Everything else is same, and on top of this what we've inserted is this y naught, okay, which is in the background. Alright, now let's compare these two together with this. We have y is equal to y naught. That means this component is 0. Okay, so what are we left with? With y is equal to y naught, we have z minus z naught is equal to a x minus x naught. From this, let's compare these two. We have our a. What's a? F prime of x naught y naught. So I've determined a. A is equal to f prime x naught y naught. Now what remains is we need to determine b. Okay, although I can just say that it's the exact same procedure, but just so that it may help students, if we go over this again, that it may help. So now let's now try to determine b. So what would we consider? We would consider L of x, and what's the slope of L of x? This is f prime of y at x naught y naught. And what are the features about this? I'm going to do this in 2D now. This is now, okay, we have y on the horizontal axis now. Now we have yz plane. Okay, this line k of x is this one. This line L of x is this one. So first feature is that along k of x and L of x, x is equal to x naught. Okay, that's the first thing I said while drawing this plane. And then looking at this in 2D, what we see is that this equation of the line Lx is z minus z naught equal to f prime by x naught y naught into y minus y naught. And with x is equal to x naught, this thing, we have this equation reduced to z minus z naught is equal to b y minus y naught, because if x is equal to x naught, this becomes 0, a disappears, and you have this is left. Comparing these two, we have b is equal to f prime of y to x naught and y naught. Okay, today I've got everything in order. Alright, so the entire session was to figure out the equation of the tangent plane, which we narrowed down to this. So I'll again use blue. Okay, and we don't need this now. Equation of tangent plane. Tangent to the function at x naught y naught f of x naught y naught or z naught, whatever you want to call it, is z naught. Actually, since we're giving this in terms of z naught, we should just use z naught here. Z minus z naught is equal to f prime of x evaluated at the same very point at which the plane is tangent into x minus x naught plus partial derivative of the function with respect to y evaluated at the very same point is y minus y naught. This is it. Okay. So that concludes the session on finding the equation of the tangent plane.